Our next speaker is Madhu Kanna, who is a professor in the Department of Ag and Consumer Economics, and she is the other co-director of CEOS. Madhu, take it away.
All right, so we're going to turn our attention now to looking at the economic and environmental benefits and costs of biofuels. This is also done with several other co-authors, and that are both here and at Iowa State and representing different disciplines. So it's a very interdisciplinary project. So just to put this in some context, this research, it's actually being presented in two papers that are hopefully going to be coming out soon. But to put this in some context, biofuels are the major sort of motivation for them was to reduce carbon emissions from the transportation sector. The transportation sector has been a growing source of these emissions, and so there's interest in looking at low carbon fuels. But because biofuels are a source of energy that requires land, they also interact with other ways that we use land for agriculture. And agriculture is a major source of nitrogen leakage, which causes a number of environmental problems, notably the problem of hypoxia in the Gulf of Mexico, but also nitrogen leaking to drinking water, groundwater, having nitrous oxides, denitrification, and so on. So nitrogen is another environmental challenge that we continue to face. So in thinking about how biofuels would interact with these two environmental problems, and there are others, but the focus of our research is looking at these two implications. It's important to recognize that biofuels is not a single thing, but they can be actually produced from a variety of different feedstocks, and these feedstocks differ in terms of their carbon intensity as well as what implication they have for nitrogen. So the ones that we consider are corn ethanol, which is primarily being produced as a biofuel in the U.S. So 15 billion gallons of that almost are being produced every year. And they have a potential to lower carbon intensity by 20 to 45% compared to gasoline, but corn is very nitrogen intensive. We can also produce biofuels from potentially from energy crops, and these are low input perennials, such as the ones shown on the right from our South farms here in Illinois. These are very high yielding, can be grown under rain-fed conditions, have significant potential to reduce carbon intensity, even being negative carbon relative to gasoline, and they can reduce nitrogen leaching and runoff from cropland. Another source is corn stover, which also has considerable potential to reduce carbon intensity, but high rates of removal can have a negative impact on soil fertility and lead to soil erosion. And they also may require additional application of nitrogen to replace the loss in soil fertility. So as we think about these different alternatives, we can see that there's going to be a trade-off between our efforts to reduce carbon intensity and reduce nitrogen runoff and leakage, and also be able to produce biofuels that are not very expensive, that are cost effective or competitive with gasoline. So this is just showing that some of the data, which just shows that, in fact, even with corn ethanol, there is the carbon intensity of gasoline is 94 grams of CO2 per megajoule. And this shows actual carbon intensity of corn ethanol produced in the US to conform with the California low carbon fuel standard. And that has considerable potential here, that this is lower than gasoline. Here is some of the studies, a study looking at the carbon intensity of different types of cellulosic biofuels, and again showing that these energy crops in particular can be negative carbon biofuels. And this is looking at the potential for these two perennial crops to reduce nitrogen runoff in the Mississippi River Basin if they were to be grown on croplands. If we were to replace 25% of the corn acres in the Midwest and the Mississippi River Basin, then you could reduce the nitrogen runoff by 8 to 10%. So large-scale production of these energy crops, particularly on corn acres, would could have an impact on the Gulf hypoxia. But of course, the ultimate environmental impact of these biofuels will depend on what mix of these are actually produced. And because these are more expensive than fossil fuels, the choice of this mix is going to depend on what policy is put in place. And so in the US, we've got the Renewable Fuel Standard that was established in 2007 with various goals, one of which was to reduce greenhouse gas emissions. And it basically set a upper limit of 15 billion gallons of corn ethanol, and mandated that we should produce 16 billion gallons of cellulosic biofuels by 2022. And there was, the basic criteria for a cellulosic biofuel is it should be from a non-food-based feedstock, and it should have at least 60% lower greenhouse gas intensity. So the graph here shows that we've actually met the 15 billion gallon corn ethanol mandate, which is the blue bars. But when it comes to the cellulosic mandate, we're woefully behind and hardly begun to produce much commercially. So the purpose of this research is to do sort of a forward-looking analysis. What if we were to extend the RFS beyond 2022 all the way to say 2030 and maintain our corn ethanol mandate at the 15 billion gallon mark and try to achieve the 16 billion gallons by 2030, what would those economic costs and benefits look like? And so in doing that, we want to look at a variety of different environmental impacts caused by these biofuels, nitrogen runoff in the Mississippi River Basin, nitrogen leakage in general from changes in land use and nitrogen application rates, greenhouse gas emissions in the US, as well as what the economic costs of this policy would be for the US agricultural and transportation sectors. And we want to separate out the impacts of corn ethanol from cellulosic ethanol. So I'm going to present results for 3 scenarios. One is a baseline. If we had stayed at the 2007 level, if we maintain this 15 billion gallons going forward to 2030 versus if we had the corn and cellulosic mandate with 15 billion gallons plus the 16 billion gallons for cellulosic biofuel, what would be the environmental impacts and the costs? And then in order to be able to compare these environmental benefits with those costs and put them all on the same playing field, we want to convert those into dollar terms as well. And so we have a method, in economics to be able to do that. So in the case of greenhouse gas emissions, there is a concept of social cost of carbon, which is the damages caused by a ton of CO2 emissions. And the value in the literature is about $50 per ton. We look at $50, and then what if it was even higher at $100 per metric ton? What would be the value of the greenhouse gas emissions saved? And we look at a variety of different changes in damages due to changes in nitrogen use. And again, there are values in the literature to look at how much of the nitrogen that is applied escapes into the environment and what are the damages, the value of the damages that are caused per kilogram of nitrogen because of its impact on drinking water and coastal zones and so on. And so every kilogram of nitrogen, the damages range in the literature from anything close to like $5 to about $17 per kilogram. And then we want to look at what are the economic costs to the agricultural consumers, fuel consumers, and the ag and fuel producers. So when we, so this is combines a integrated approach which links a hydrological model with an economic model in order to do this impact assessment. And I'm going to just give you the sort of bottom line results that we get. So what we find is that maintaining this 15 billion gallons of corn ethanol would reduce the total greenhouse gas emissions from the agriculture and the transportation sector by about 3% over the next 15 years or so. And adding on the 16 billion gallons further reduces emissions by another 4% or so. So together, they can have a significant effect of reducing total emissions by 7% over this time period. But when it comes to nitrogen, it's a much more of a mixed story, because what we find is that actually the corn ethanol mandate, because it'll expand land under corn production, it is going to worsen the hypoxia problem. It's going to increase the nitrogen leaching by 8%. And then surprisingly, what we also found is that with the addition of the 16 billion gallon cellulosic mandate, there's actually a further increase in the amount of nitrogen leaching that would take place. So there would be another 8% increase in nitrogen leaching. And so we were sort of puzzling over why that was. And when we kind of looked into it further, what we found is that a major reason for that is because quite a substantial part of that cellulosic ethanol mandate would be met by corn stover. And removal of corn stover can have a detrimental impact on the amount of nitrogen runoff. So if for, in a hypothetical case, if we were to meet that entire mandate with only perennials, then in fact, the amount of total runoff would be lower than what we have even with the corn ethanol mandate. So we might actually begin to offset the damages due to corn ethanol. Or if we reduce the amount of nitrogen, replacement nitrogen applied to corn stover, we could also reduce the amount of runoff. But without those constraints, there'd actually be an increase in the problem of hypoxia. Then we added up all the other nitrogen impacts as well, and I'll get to that in a minute. But so here we looked at what are the total economic impacts across different sectors, looking at the agricultural sector, consumers, producers, and transportation sector, and so on. And what we find is that, with the corn ethanol mandate, the key group that benefits from that is the agricultural producers, and that's largely because the mandate raises the price of food crops. And correspondingly, there is a cost to the agricultural consumers who have to pay higher food crop prices. Of course, this is much smaller with the addition of the cellulosic mandate, because that has a much less negative impact on food crop prices, and therefore has a lower benefits for agricultural producers, but there is still a benefit to them. The cost of the mandate in terms of is borne by the fuel consumers, and so that's sort of the negative here. There's in the current model, there's not too much of a negative impact on the fuel producers. Looking at the environmental benefits, so there's a benefit in terms of greenhouse gas emissions, larger in the case of the cellulosic mandate than the corn ethanol mandate, and nitrogen damages, which are really significant in the case of the corn ethanol mandate. So at the bottom line is that both mandates impose net costs on the economy, taking into account both economic and environmental consequences. These costs are much larger with the corn ethanol mandate, but negative also with the cellulosic mandate. So what does all that mean? Well, what that implies is that, there's several factors here that affect, this is one estimate, and we look at a variety of different other scenarios. But in general, what we can sort of take away from this is that these biofuels do have a potential to reduce greenhouse gas emissions, but their overall costs and benefits will depend on a number of different factors. A key one in that is going to be the price of oil. As the price of oil is lower, the greater the cost of trying to impose higher cost biofuels on the economy. In the case of cellulosic biofuels, which are still under production, and their commercial competitiveness is, we're still to get to that point. What technological improvements take place will also influence the ultimate economic cost of using them. And then the value that we associate with the emissions reduction and the nitrogen damages that are caused will also impact how much we value overall having biofuels in the mix of fuels